Good afternoon, everyone. My survey is titled When Should a Recognition System Refuse to Classify? So, the core question is instead of always outputting an answer, when should a classifier just say, I don't know, or this input is not something I should be making a call on? And I won't argue that this ability is not a nice to have. It is fundamental to what it means to be a reliable recognition system. So let's start with motivation. The standard classifier is basically a total function. You give it any input, it gives you a class label. That sounds fine, but think about what that actually means in practice. Take a handwritten digit recognizer. Suppose someone writes a 3 that looks really similar to an 8. These posteriors over those two classes are like 50-50. A standard classifier still has to pick one, and it does, but that pick is really just a coin flip. The confidence is not there to back it up. Or consider a completely different scenario. A sensor input comes in that is outside anything the model has been during training, like an object category that never appeared. The model has no legitimate basis to classify it, but in forced classification mode, it will still output something, often with high confidence, because that is just what softmax does. In both cases, standard accuracy metrics make this invisible. You only measure whether this classifier was right, not whether it had any business making the call. So this survey is organized around two structurally different reasons to refuse. The first is ambiguity rejection. The input is in distribution, but the evidence is weak or conflicting among non-classes. The second is novelty rejection. The input falls outside the scope of non-categories entirely. These are different problems and they require different tools. The core thesis is refusal is not an optional add-on you put on after building a classifier. It is intrinsic to any honest recognition system. The survey covers classical pattern recognition and statistical decision theory. It is not primarily about modern deep learning heuristics. It's about the fundamental theory that lets you understand what those heuristics are actually doing. The organizing axis for the whole survey is the ambiguity versus novelty distinction. And a key claim I want to establish is that modern open set recognition and OOD detection are continuations of these classical problems, not independent use of fields. If you understand the classical theory, you understand where the modern work fits. Let's formalize this. In the standard setup, classification is an action selection problem. The action set is just 1 to k, one action per class. The best optimal solution on the 0-1 loss is to pick the argmax of the posterior. That is the standard story. Now we can add one action, reject. The new action set is 1 to k to reject. To make this sensible, we assign the rejection action a cost, C to R, where C to R is strictly between 0 and k minus 1 over k. That constraint means rejection is cheaper than the worst misclassification, but more costly than correct classification. So rejection is always better than random guessing, but you would never prefer to reject if you are actually confident. The overall risk is the probability of error plus C to R times the probability of rejection. You want to minimize that. Now that framing rests on three assumptions that become the research agenda for the rest of the survey. First, inputs belong to known classes. Second, posteriors are calibrated. Third, costs are uniform. When assumption 1 breaks down, you need novelty rejection. When assumption 2 breaks down, Joe's threshold becomes unreliable. When assumption 3 breaks down, you need class-dependent threshold. Each failure generates a distinct research threat. Given that cost structure, Joe derived the optimal rule in 1970. It is classified as arcmax of the posterior if that maximum posterior is at least 1 minus c to r and reject otherwise. So the decision boundary is just the threshold on the maximum posterior probability. If your confidence in the best class clears that threshold, classify. If not, abstain. Two things make this result really important. First, Joe proved it is Bayes optimal. No other deterministic rule achieves a lower expected cost for the same reject penalty. You literally cannot do better than this rule, as long as you have calibrated posteriors and a fixed cost. And second, the rule is model independent. It does not care whether your classifier is an SVM, a neural net, or a nearest neighbor rule. As long as you can produce posterior estimates, the threshold logic applies. Hillman extended this to nearest neighbor classifiers in the same year, using local class distribution among neighbors as a proxy for the posterior. The key point from Hillman is that rejection is a property of the decision problem, not of any specific model family. Any classifier that gives you a confidence measure can be equipped with a reject option. The one requirement is reliable posteriors, and that requirement is exactly where things get complicated in practice. As you vary the rejection cost C to R, you sweep a curve in error rate versus rejection rate space. That curve is a monotone parallel frontier. Lower error is only available at the price of higher rejection. You cannot have both at once, which is intuitive. That is, the more selective you are, the more you reject. The curve goes beyond the Bayes error rate at zero rejection, meaning that you classify everything down to zero error when you reject everything. The shape is concave. And as C2R decreases, the confidence threshold rises, the reject region expands, and the error rate on classified inputs goes down. You are being picker about what you classify. And the primary evaluation tool for classifier with a reject option is the accuracy rejection curve, or ARC. It plots accuracy on accepted inputs against rejection rate. A good rejection mechanism should make accuracy improve smoothly and sharply as you reject more. That curve summarizes the overall quality of the rejection system. The decades after Joe produced a coherent set of generalizations, each relaxing one assumption of the original rule, Hillman extended to nearest neighbor classifiers, establishing that framework is model independent. Ha generalized the output from binary, either classify or reject, to set valued. You output a subset of plausible classes rather than one label or nothing. The cost depends on the set size and whether the true class is included. This anticipates modern conformal prediction, though Ha developed it entirely within the Bayesian cost framework. Fiumara and Torotella addressed class-dependent costs. Different classes have different misclassification costs, so optimal rejection threshold should differ per class. Tortorella derived this in the ROC plane, which is useful because you do not need explicit posteriors to set the threshold. And most importantly, Dubition and Mason in 1993 formally separated ambiguity rejection from distance-based rejection. They recognized that the posterior base threshold is insufficient when inputs fall outside the training distribution because posteriors can extrapolate high values into regions the model has never seen. This is the first formal articulation of the ambiguity versus novelty distinction. Zhou's rule assumes you have the true posteriors. In practice, you estimate them, and estimation errors flow directly into rejection errors. So Bartlett and Webcamp in 2008 asked, can we learn the reject rule jointly with the classifier using a convex surrogate loss? The answer is yes, and the tool is double hinge loss. The idea is to add a flat abstention interval around zero margin. If the margin is strongly positive, classify correctly. If it is strongly negative, classify the other way. If the margin is in a middle zone, neither classification nor rejection is penalized. So that flat region in this loss surface creates the abstention region. The key theoretical property is Fisher consistency, which is also called classification calibration. Minimizing this convex surrogate gives you the best optimal classifier and the best optimal reject region at the same time. So you are not estimating posteriors and then thresholding separately. You are learning both jointly from the data. Next, Frank and other people later showed something really clean. 3 different ways of formulating the rejection problem: cost-based like Zhou, coverage constraint like Yaniv and Wiener, and accuracy bounded all lead to the same optimal strategy. So the different formulations are not in conflict. They are equivalent perspectives on the same underlying problem. Here's what the practical story gets complicated. The obvious approach for deep networks is to use softmax confidence as the rejection signal. And that means if the softmax output is below some threshold, reject. Simple and model-free. But it fails because of a fundamental property of modern networks. Guo and other people in 2017 showed that deep networks are systematically overconfident. They output softmax values close to 1.0 even for incorrect predictions. So the high confidence does not imply high accuracy. A handwritten digit the network is about to misclassify might still get a softmax output of 0.97. If you threshold on that, you accept the wrong prediction. This is why Zhou's style thresholding on raw softmax basically does not work for deep networks. And there are a few responses. Temperature scaling rescales the logits to make the softmax less big. That helps calibration, but does not fully solve the rejection problem, because what you need for good rejection is a signal that ranks correct versus incorrect predictions, not just calibrated probabilities. So Frank and Prusa took a different approach. Train a separate branch to directly predict misclassification probability. You are no longer asking how confident is the classifier, you are asking how likely is this specific prediction to be wrong. That is a more targeted signal. And Jiang and other people introduced trust scores, which use local density in the feature space. If the classifier's prediction agrees with the nearest neighbor, say, trust it. If there is a disagreement between the classifier and the local data structure, reject. This works because it bypasses the miscollaborated softmax entirely. Yaniv and Wiener in 2010 gave the finite sample formalization of this work. A selective classifier is a pair. a predictor f, and a selection function g. The predictor maps inputs to class labels. The selection function maps into inputs to 0 or 1, where 1 means accept and 0 means reject. Selective risk is the expected loss computed only over accepted inputs. So, it is the conditional error rate on the subset you decide to classify. Coverage is the probability mass of the accepted region, like what fraction of inputs you are willing to classify. The goal is to maximize coverage subject to a risk constraint. You want to classify as many inputs as possible while keeping the error rate on those inputs below some target level. Yaniv and Winner proved PAC-style guarantees. Given a confidence parameter, you can compute a certified coverage risk curve. That is what makes this framework deployable rather than just theoretically nice. In the deep learning era, selective classifiers have evolved through 3 conceptual stages. The baseline is post hoc softmax thresholding. You take a standard trained network, use the max softmax probability as the selection score, and set a threshold. Simple, not retraining needed, but limited by miscalibration. And the second stage is auxiliary networks, like COFFEE-net. You train a separate model specifically to predict failure probability. That is, whether the main classifier will be run on this input. The decoupling is important. Classification and confidence estimation are no longer the same head. And the third stage is integrated selection, like selective-net. This is an end-to-end architecture that jointly optimizes classification and selection under an explicit coverage constraint. This network learns to accept only what it can classify safely. You are not post-processing a confidence score. Instead, you are learning what to accept as part of the training objective itself. So each stage replaces a generic heuristic with a more targeted principled mechanism. Up to here, all the tools have been about ambiguity rejection. Inputs are in distribution, but uncertain among known classes. Now we shift to novelty rejection, which asks a completely different question. It's not which class is this, but does this input belong to the problem at all? One-class classification learns a description of the training data support in feature space. The 2 classical tools are the one-class SVM and SVDD, support vector data description. One-class SVM separates the training data from the origin in a kernel feature space. SVDD finds the minimum enclosing hypersphere around the training data. In both cases, the boundary defines what normal looks like. Inputs inside are accepted. Inputs outside are rejected as novel. So the key insight is that novelty is a distance from the non-data region, not uncertainty in the posterior. A novel input might actually trigger high posterior confidence in the wrong class, but it will be outside the learned hypersphere. That is why this machinery is necessary alongside posterior-based rejection, not instead of it. Deep SBDD by Ruff and other people in 2018 extends this to learned representations. So the hypersphere is fit in a deep network's feature space rather than a fixed kernel space. This is the conceptual center of the survey, and I want to go through it carefully. The table compares the 2 forms of rejection along 5 dimensions. First, the input location. Ambiguity rejection operates on inputs inside the training distribution among known classes. Novelty rejection operates on inputs outside it entirely. Second is triggering signal. For ambiguity, the signal is a flat or uncertain posterior probability. For novelty, the signal is a distance from the known data region. Third is foundational tool. Joe's posterior threshold for ambiguity, one class classification like SVGD or one class SVM for novelty. Fourth is failure mode. Ambiguity rejection fails by confusing two known classes, like a 3 that looks like an 8. Novelty rejection fails by classifying an unknown input with false confidence. That is because the model extrapolates. And the evaluation metric, error reject trade-off curves and ARC for ambiguity, false positive and false negative rates on novelty for novelty rejection. The critical theoretical point is that no threshold rule on posteriors is sufficient for novelty rejection. That is because posteriors outside the training support are extrapolations. Those extrapolated values carry no probabilistic warrant. So you cannot use a tool designed for one problem to solve the other, and that is why these two mechanisms need to coexist in a robust system. Let me show concretely why you need both, not just one. Let's consider a system with only ambiguity rejection, like a standard classifier with Joe's rule. Works great when inputs are among known classes, but when a novel input comes in from outside the training distribution, the model extrapolates. And deep networks in particular tend to assign high posterior confidence during extrapolation. So the threshold is cleared and the input is wrongly accepted. The posterior check is not just unhelpful here, it is actively misleading. Now let's consider a system with only novelty rejection, like a pure one-class classifier or SVDD. Works great for detecting out-of-distribution inputs. But what about an input inside the training distribution that sits on the boundary between two known classes? SVDD accepts it because it is inside the hypersphere, but the classification is still ambiguous. Without posterior analysis, that ambiguity is invisible. So the two failure modes are dual. Ambiguity-only systems fail on novel inputs. Novelty-only systems fail on ambiguous but known inputs. A robust system needs both pathways running in parallel. Posterior analysis for uncertainty among known classes and boundary modeling for inputs outside learned scope. These are not competing approaches. They are complementary ones addressing fundamentally different failure modes. Open set recognition, or OSR, extends the classical framework to settings where unknown classes appeared at last time. The key formal contribution is the concept of open space risk. The risk of assigning a non-class label to empty feature space, regions never near a training point. Minimizing open space risk means compressing decision regions to be more compact around training data, converting classification boundaries into tighter recognition boundaries. That is conceptually the same thing as VDD does. An important empirical finding from Bayes and other people in 2022. That is, well-trained closed-set classifiers with simple MSB thresholding often match or beat specialized OSR methods. This confirms the classical principle. A strong representation plus a principal rejection threshold is often all you need. The takeaway is to treat open set recognition as a boundary condition of the classical rejection problem, not a fundamentally new paradigm. OOD detection is a repurposing of classical rejection principles to the setting where the test distribution differs from training. The key insight is that confidence scores and uncertainty estimates become rejection signals. The MSP baseline from Hendricks and Jimpo in 2017 uses softmax probability as a proxy for Joe's threshold. Simple and surprisingly effective. The energy score from Liu and other people in 2020 uses long-sum expert prediction of logits instead, which aligns better with input density than softmax and improves detection. For the epistemic uncertainty, MC dropout and deep ensembles approximate Bayesian posteriors through stochastic passes or ensemble disagreement. High epistemic uncertainty serves as a direct signal for novelty rejection. The model does not have enough information in this representation to make a confident prediction about this type of input. The synthesis argument is worth stating explicitly. Modern uncertainty quantification is essentially trying to recover the calibrated posteriors that Joe's rule requires. That is the fundamental goal of temperature scaling, conformal prediction, and trust scores. The framework has not changed. The problem is recovering the inputs Joe assumed. Selective net is L. Yaniv and Winner's risk coverage framework implemented with learned features and a differentiable coverage constraint. Deep SVDD is tags and doing static description with a neural network representation instead of a fixed kernel. Different architectures, same underlying decision problem. And a good closed set principle confirmed by Bayes validates the continuity thesis. You do not need exotic new machinery. A strong classifier with principal rejection is already most of what you need. The two pathways, posterior base for ambiguity and boundary base for novelty, remain the essential organizing principle. Let me flag the 6 open problems the survey identifies. 1. Unified rejection architectures. No existing framework optimally fuses ambiguity and novelty rejection under a single objective. Combining selective net and deep SVDD end-to-end is open. 2. Calibration-free rejection. Conformal prediction offers distribution-free coverage guarantees without calibration, and extending that to the reject option is active. 3. Learning to defer to humans. The reject action can become a defer action, routing uncertain inputs to a human expert. This requires jointly modeling expert competence alongside classifier uncertainty. 4. Reject option for foundation models. When a language model should say, I don't know, it's actually the same question. Connecting decision theoretic rejection to hallucination detection is largely unexplored. 5. Continual and open world learning. Novel inputs should trigger model updates rather than permanent abstention. Rejection becomes a signal for adaptation. 6. Theoretical gaps in deep selective classification. Yaniv and Winner's PAC guarantees apply to fixed hypothesis classes. Extending them to over-parameterized deep networks is still open. So let me close with the answer to the title question. When should a recognition system refuse to classify? There are 2 situations. Refuse when the evidence is insufficient among known classes. That is ambiguity rejection, and Joe's rule from 1970 gives you the optimal strategy. Threshold on the maximum posterior with the threshold set by the cost of rejection. Refuse when the input is outside the scope of what the system has learned. That is novelty rejection, and it requires boundary-based methods like one-class classification because posteriors outside the training support are meaningless extrapolations. But both are necessary. Neither is sufficient alone. Only conflicting them leads to silent failures. And the classical theory, statistical decision theory, and the risk coverage framework provides the optimality conditions and guarantees that modern heuristics often lack. Modern methods are extensions and implementations of these classical ideas, not replacements for them. Thank you for your listening.